Hello, good evening, and really a warm, hearty welcome to the Bay Area Apache Spark Meetup on the eve of the 10th Spark Summit. My name is Jules Damji. I'm the Spark Community Evangelist for Databricks. And for those of you who are here also for the Spark Summit, delighted to be here to see all of you here for our 10th Spark Summit. It's actually a momentous moment to have the Apache Spark community reach its 10th Spark Summit. You know, I remember with actually quite fondness, 4 years ago when we had our first Spark Summit, it was in Hotel Nico in San Francisco, and it was a small affair. You know, we had one small room, we had 2 tracks, and in one day it was all over. And today, you know, we had in San Francisco, it's a huge heartening to actually see so many of you actually here for the meetup as well. And many of you here have contributed quite a bit to Apache Spark. As of this morning, you know, it's because of the community like you, it's because of people like you who actually keep Spark going. It's people who are actually out there adopting, advancing, and advocating. And those of you who are presenting or talking about Spark in the community, this is what is actually making the Spark community a huge global movement. This morning I checked at this meetup on Spark. We've got 625 meetups groups around the world with about 375,000 members all around globally. Remember that, 610 meetups group with 375,000 members around. It's all because of you, so give your hand a big hand. And in many ways, you all are really advocates because you are really contributing to this, what I call really the Spark moment. And the fact that you're here for the 10th Spark Summit really heartens me as being one of the advocates for the community. So thank you all for coming. Now, before we actually get started, I have some announcements to make. Those of you who actually came here earlier, we had some slides up on the screen. Some of you actually missed it because the food was outside. It was great. We're going to be having 7 BOF sessions, birds of feather, for those of you who are old-timers like myself. Throughout the lunch in the Spark Summit, there'll be tables around. They will actually have signage up at the top that announces what the themes and topics are. So if you're interested in that, we're going to have 4 the first day and 3 the next day. Join the conversation, ruffle some feathers, should be fun. By demand, there's going to be a luncheon here on June the 7th for Women in Data, Big Data. A lot of luminaries will be there talking about how machine learning and how big data is actually changing the landscape. So do come by, look at the schedule. I think it's around 12:30 in this particular room. And obviously, no Spark Summit is without a huge party. And this is the first time to celebrate the 10th Spark Summit. We're going to have a join party. What a geeky name. What do you expect? We're going to left join, right join. It's going to be fun. Anyway, so do stop by. It's at 44 JC Street, 8 p.m. on Wednesday, and it's at the Mezzanine Restaurant. So do stop by. Now, I have one minor regretful announcement. We were supposed to have a panel of Databricks Spark committers over here towards the end of the meetup to talk about AMA, ask you anything about Spark. However, they are, as of last minute, a text I got, feverishly working upstairs in the war room to finish up some things, surprises for tomorrow's keynote. So regrettably, they won't be here. So I apologize on their behalf. They won't be here. However, they're going to be at the office hours at the booth. So do stop by if you have any heart-burning questions you're going to ask them about Spark, about where Spark is going. They should be there. It should be a very informal session to do that. Now, a couple of acknowledgements. I do want to thank the Spark committee organizing to give us this particular room. And a huge thanks to Pepper Data, who actually are sponsoring this particular event and provided all the food out there. So thanks a lot, and give them a big hand to Pepper Data. Now, just to kick off today's meetup, we have our first speaker from Pepper Data. His name is Sean Suchter. He is the CTO and the co-founder. Now, many of you have actually worked with Spark before. You know, it's a huge distributed computing engine, and there are a lot of different things within that. You got schedulers, you got masters, you got drivers, you got tasks, you got shuffles going on. And understanding and getting a glimpse and getting a pulse of how these are performing and how they're being tuned actually gives you quite insight into how your Spark job is going to fare over a period of time. And to tell us all about that is Sean Suchter. He's going to talk about how to performance tuning some of your Spark engines. So give a big hand to Sean.
Thanks, Jules. And thanks, everyone, for coming here and being here at the summit and the meetup. So I'm going to talk about Spark performance and specifically how to debug it it's hard, that is hard. Spark in general is really powerful. It hides a lot of things under its abstractions for you. That's great. On the other hand, the fact, debugging performance of it, since it hides all these things under its abstractions, gets hard. Let's see if we can make that a little easier. Just a tiny bit about our company. So Pepperdata is purely focused on performance for big data. So we are installed on over 15,000 production nodes. We see over 50 million jobs a year. This translates into, at the last count, 200 trillion performance data points. And the key is that, as part of our offering for many of our customers, we're actually watching all of this telemetry, and we're using this to, find different patterns and find conditions to make products and, find insights like some of the things I'm going to talk about today. So things I'm going to talk about, right? First, I'm going to cover basically how Spark code translates into the execution of the applications. That's basic foundational stuff that's really important to get into some of the more detail I talk about later. I'm going to talk about how to, some very common and known problems, but the things that keep hitting people over and over, and what's some easy ways to find those. Then I'm going to talk about the hard case, right? For the ones where it's not the common case, it's not the thing that you see every day. What kind of data you need in order to see into those hard cases, currently from separate tools. And then I'm also going to show what it looks like if you put these things together and why that's of high utility. So the first thing is basically some brief basic terminology about Spark, right? A Spark application is composed of multiple jobs. Each job may have multiple stages. And then each stage is composed of multiple tasks. And that very lowest layer, the tasks, is what actually runs on the executor, right? So the executors are the processes that actually do the work, and they're composed of, they compose their work of tasks, and everything above here is kind of an abstraction that, you just deal with this, and Spark magically makes all of this happen for you. And let's look at how that happens a little bit. So here's an example, basically very simple application. It's a hello world kind of equivalent, word count, right? For some reason, that's the hello world of big data. And it's basically got the common pattern for a Spark job. It declares some input, right, from external storage. That's this first line. Give me a text file. Then it specifies some transformations. Right? Here we're going to do some transformations on the file. We're going to look at all the lines and split them into words, and then we're going to just say that, well, that line had one of each of those words, and then we're going to reduce them by the word key, and we're going to add up all those counts. So that's a word count. And then the last thing is that you trigger an action. Right? In this case, it's save it to a text file. And that triggering an action is super important in Spark, because that's when you actually make an action, materialize the data somehow to your console or to a file, this is when this all actually gets translated into a job and stages and tasks and gets sent out to the executors. So Spark has this distributed architecture, right, where the driver gets to get some instruction basically from that program that you made, and then sends these tasks out to all these processes that then run them. And this is where the power comes from, because you can obviously process huge amounts of data very, very quickly in Spark. It's also where this complexity comes from, because you don't know exactly how it did that. What it actually did to translate this out and where it sent them all. So here's the same program, right? And here's some details on how it translated into an actual execution plan, right? And so in this case, my program here translated into 2 stages. The first stage had the input, the text file command. You see that from there. The second stage took all the lines and translated them into words. And then the third stage, said, hey, we're gonna take and use the word as the new key. And then the last stage here, the stage number 1, takes all of those words, adds them up, so we get a global count of words across the application. And the key thing, unintended, the important thing here between these two is that this first stage, you see it has multiple operations on it. but they're all using the same key, which is the line, right? So the key space is all the same in this first stage. And then as soon as we go into words as our key space, it goes into a new stage, right? So when we went from lines to words, that triggered going into a new stage. And in Spark, this is called a wide transformation. But the important thing is that multiple things in your program here are all bundled together, and they're divided into stages. And in between these two, right, whenever you do a key space change like that, that's when you have a shuffle, right? And so the shuffle in this case kind of looks like this. There's a bunch of lines that are processed by different tasks in parallel. So your input file is read, and in parallel, all the different lines are processed. And then they're turned into words, and all those words are sent to new tasks that may or may not be the same executors. And in fact, almost always, most of the data will have to be shuffled to different executors, perhaps from the same set of them, but they'll have to be shuffled around because you want to reuse all those executors. And then these guys count up the words, and you get a result that in our job got written to disk. So this is the last thing on the background. This is an example of how this basically got divided up. We can see that in this first stage, there's multiple tasks here, and the first task, this first partition, is processing all of the things from reading the data, reading the lines, splitting them into words, and then saying, hey, the word is going to be our new key. And so every different part of the file is able to be processed in parallel. And then it gets sent to the stage one, which is doing our reduction, and then finally writing the thing out. And then there's a new set of tasks for this one. So you get a linear thing of tasks that has been divided up between all these things. So now let's talk about some problems. So the easy case is debugging known problems, things that you've seen before, things that are common patterns that happen a lot. So the first place that you normally look is the Spark history server. Right? People, this is something that probably a lot of people here are somewhat familiar with. And it gives you a list of applications, right? Starting in Spark 2.1, you can actually do a search on that. You can drill into any one of these applications, right? You find the one that you're interested in, you can click on it and get lots of information about this application. Lots of, like a whole bunch of information. There's some stuff that's currently missing. For example, especially performance affecting things like Spark, since it has this complex computation model, it can divide up your application into all these stages, and it knows the dependencies between them. And it turns out that one of them could fail in the middle, and Spark might retry it, and it might succeed again, and then your app succeeds. So if your app totally fails, it'll be highlighted here. But if your app succeeds and is just slower because one of them retried, one of the stages or one of the tasks retried, that actually doesn't highlight at all. So it just seems like it's a little slower. So when you click into one of these applications, you see a whole bunch of information about, you basically got a whole bunch of information about the performance counters and things like that from the application. It's a lot of information. If you've got a very trained eye, and you've seen this many times, you might see some pattern here of what's wrong. Clearly, it's obvious from this page, exactly what's wrong. Perhaps not. The main thing is that this doesn't really tell you a lot about what to think about the data. It provides a lot of really useful data, no doubt, but it doesn't render any opinions on it, and that's okay because it's not the job of this system. So let's talk about a thing that we can do about it, right? So this is intro into a project that came out of LinkedIn. Called Dr. Elephant, and this is the UI for MapReduce from Dr. Elephant, and it's been around for many years. And it basically, you see all these little pills here. You don't have to read the content here, but the important thing is each one of these little things here is basically a heuristic that renders an opinion that says, hey, this job, and green means good in this case, like on this aspect of what we know to look at for the jobs, it means it's doing well. And you can see it's clearly saying, these jobs have a problem in this one attribute, right? And you can click on that and get more information. So Dr. Elephant is what is it for? It is a performance monitoring and tuning system, right? It finds common mistakes, and it suggests what you should do about it. In the last few months, Dr. Elephant has actually been enhanced to have application level heuristics for Spark, right? Which is very useful, right? So, there's not as many things, there's not as many little pills here. That's getting, those keep getting expanded. But, here in a few Spark applications, we can see that it has an opinion. There's something wrong in these jobs in particular ways. And if you click on one of them, you get more information that's tailored to what it actually thinks is wrong. And if you click on one of these explain links, it gives you a very detailed thing. It says, we think that this application is wrong in this way. Please change this thing. Right? So there's a set of things that it knows about. So there's 3 main classes of heuristics in Dr. Elephant for Spark right now. Basically, configuration settings, things that might be wrong in the configuration of your job. These apply regardless of what your input data is. And they catch basically mistakes, silly mistakes in config, or highlight things that are best practices to use. There are alarms based upon stage or job failures. This is very basic, but it's catching, especially if you have hundreds or thousands of jobs you're running, it's really useful to have something to say, hey, this one's slow because something failed in the middle and it retried it. You don't always know the root cause here, but it's at least point in the middle of that sea of things to point out, look at this one. And then the last one is very data-dependent tuning suggestions. And this is one where maybe you had your job tuned well at the beginning when you first wrote it, but then you've been running it for months, and hey, maybe it's not so great anymore, and we can catch why it's not great, right? Because there's something to look at right here. And so this thing where it's useful to keep looking at the execution of the job every time and see if the data and how it's laying out on those tasks and executors, if it's still a very optimal configuration. Briefly about the 3, the existing ones. Configuration heuristic, basically shows you some config settings. It'll complain if some important settings are not explicitly set. And it recommends some best practices. For example, it might recommend configuring an external shuffle service. And this is especially important if you're using Spark dynamic allocation. There's also a few other things like, for example, it'll recommend using the cryo serializer, which we believe is currently the fastest serializer. So if you care about performance, use that one. And in general, these just don't change over time, right? Your application, if you've got it set right, these aren't going to break. The stages and jobs heuristic, very simple. Basically say when there's a failure, where it is, and where you might look to fix it. And then the last one, is in Dr. Elephant. It's called the executors heuristic, but this is one that is tuned at the data and how it's laid out, your tasks and in your stages, and how it's laying out against your executors. So it looks at a few different counters and metrics and how they're distributed across your executors. Like it looks at, how much data is getting fed into each one, how much data is getting shuffled, how long are they taking, how much memory are they using, and if there's a significant amount of skew, that's something you can do something about. The most common way to do something about it, which it will suggest, may be to modify your number of partitions. If you have a few more partitions, then things may get evened out over the cluster. So one that we're working on right now is something we're calling the partitions heuristic. This is not yet in, but it's getting worked on. So this is something where, for performance, you ideally want to have the temporary data that each task uses. It would be nice if it fit into RAM. Now, Spark will handle it if it doesn't. It'll spill the data out to disk cleanly and transparently for you, but it'll just translate into a little bit of a slower execution. So there, Sandy Riza, who was at Cloudera, had an excellent blog on Spark tuning. We linked to it at the bottom. But basically, he found all the factors that might affect your RAM, and has a nice formula. And this heuristic will basically apply that formula to your jobs and say, hey, is this a good tune? Can we have more heuristics? Well, yes, we can. Dr. Elephant is open source, so if you have a idea of a heuristic, or if you want to actually implement one and contribute it, please do so. Come. Here's the GitHub, and please suggest something, or actually suggest code if you'd like. Other thing I have to say, is there an enterprise version of this? Well, why, yes, there is. It's the Pepper Data Application Profiler, which is one of the reasons I know about this. It provides the similar benefits. It's got some additional enhancements. It's mainly trying to make it very simple to get the simple answers to the simple questions, but it also has more data available for if you're a real expert user to be able to do combinations of complex questions. But for everybody, we're trying to provide some really actionable insights. It's also very simple to install and comes with our support. We're deliberately keeping the heuristic code base very close to the open source so that both we can take advantage of changes in the open source, but also take the advantage of the data that we have, that we're collecting, and when we develop heuristics, contribute them back to the open source. This is basically what the application profiler looks like. It's got a bunch of ways to select what you're looking at, search for different jobs, classify things as to how critical they are, and you can do things like look at more complex time series data that the core Dr. Elephant doesn't look at yet. So the next thing I'm going to talk about is debugging some hard and novel problems. This is things that are patterns that you haven't seen easily before, and you have to look at more data. Now, this is frequently the hard case that you spend a lot more time on. There are two reasons why this is a hard problem. The first reason is that the same external symptom, which is almost always the same symptom, my job is too slow. That's everybody, it's slow. It was fast yesterday, but now it's slow today, or something of that can be caused by many different root problems. It can be the code being, having a problem. Something might have changed in your data. Maybe you have something wrong in your configuration, or maybe it's not your fault and it's the cluster weather. Something else happened that is slowing down your application. Then the second problem is that the existing tools, especially in isolation, have some limited visibility. Spark Web UI is certainly a very popular tool, and it's extremely important as a starting place. It gives you a good view of that query execution plan, right? Like how how your application got laid out into jobs and stages and tasks. And it provides you this limited aggregate view of some performance data. It basically provides you some aggregate counters. What it doesn't provide you is any kind of time series information. It doesn't give you an understanding of that. Things like Ganglia or Embari, Cloud Manager, et cetera, can provide you with some time series data for your cluster. Of course, those are overall for the cluster and don't really provide you data just for your Spark application, which might actually be what you want. You can take some Spark sync data and feed this into things like InfluxDB or some other things, and this will give you some Spark application metrics. But it certainly won't give you a view of the entire cluster. In general, right, certainly these two things, the web UI and the time series, your code execution is not tied to your resource consumption, right? And you definitely can't see other applications in any of these, right? That's basically not accounted for. And to debug these complex problems, you need to know all of these together. So there are three things that you really need. You need to know that code execution plan, right, to indicate which block of code is being executed and maybe where it's being executed. And then you also need to have a time series view, right, a visual way to see how these resources are getting used. Our brains are really good at looking at a visual pattern and saying, right there, I'm going to look at it right there. This is where the problem is, right? And then you also need to be able to quickly see the cluster weather, right? Because you definitely don't want to spend a lot of time saying, what changed in my application? Why did it go slower today when it actually wasn't your application at all? It was the other thing, right? Because you could waste a lot of, I have seen people waste a lot of time in that kind of thing. That's why we do it. So the first half of this, the Spark Web UI, let's look at that. So it gives you a very clear, execution plan, right? This is, here is how my individual bits of code, right, translated into different stages, and some aggregate counters about the execution during those stages. The next thing it gives you is you can click into one of these and you can actually see the individual executors, right? That has some, some usefulness. And in this, and it gives you some aggregate counters about how the executors were used in a given context. Of course, these are aggregates and totals. There's no time series here. But it does render a little bit of opinion on things, which can be useful. Like in this example, it highlighted, hey, there's the GC time, right? So there's a heuristic in the Spark UI that says, hey, this GC time maybe took a little more time than I wanted it to for the length of this job. So, I'm going to highlight that to you to say, hey, this took a while. Maybe you ought to look at that. The problem is you don't know exactly what to do about that except for maybe just give it more memory, which may or may not be the right answer. So let's look at the second half of the solution. We'd like to have a time series view. So here's, of the same application we were just looking at Spark UI, here's a time series view. And this is how basic metrics, CPU, memory, garbage collection, HDFS were getting used. This is actually a plot out of the Pepper Data cluster analyzer, which has the ability to look at individual applications, which is useful for this example. But my main point is not that product, but just that you can actually get some value out of looking at the individual application in a time series way. And in this case, right, for example, we might notice that yes, there is a fair amount of GC, and in particular, there's a big storm of GC here towards the end. So that would be useful to look at. The problem here is, well, what I'd really like to know is, well, what code was doing this? Right? What code was going on at the time where the GCs went nuts? Right? And so I need that other thing that I just saw. So now let's, the best of both worlds, let's bring them together. And so this is what it looks like when it's together. Yes, this is our new product, the code analyzer for Apache Spark. And it's basically takes together and say, hey, let's look at an execution plan along with the time series. So in this case, I can see here's the different stages and when they're running. And I can see, and here this is a plot of CPU, so it's the same chart that we saw on the previous thing, and how the CPU pattern was going on during the various stages. But of course, I don't want to look at CPU. I actually want to look at garbage collection, so let's switch it and turn on garbage collection. And so we can see that same chart as garbage collection. And we can see that big storm. Oh, it was all during this one stage, right? Let's look at that. It's all during this one stage 4. Ah, okay. Well, so now I want to look at stage 4, right? Here's, I can actually look at my code, but in this case, I might click on here and show, what the hardware was actually doing during stage 4. So I can see, if I click on that, I get to here, where now I can see, here's all the executors that ran something for stage 4. And here's, by executor, how were they using CPU and heap and garbage collection? And indeed, I can see some garbage collection. I also notice in the individual executor here, this is a list of the executors. And if I look at them, I see, hey, this first one here, it took a lot longer than all the rest. And actually, well, it had twice as many tasks, so maybe it's not too surprising that it took a lot longer than all the rest, right? I can highlight this one, and now I look and I see, the garbage collection, right, this big amount of garbage collection was from that executor, and it was because it tried to do twice as much stuff. And so, yes, perhaps giving my job more memory might alleviate the garbage collection, but actually that probably wouldn't compress the time very much, because the main part of the time was just that this executor was doing twice as much work as the other one, right? So in this case, distributing your, making a few more tasks, making a few more partitions might actually reduce the time a lot more than throwing memory at the problem. And this is a very hard thing to find. Which stage, where's the problem, if you don't look at, the resource consumption and the execution plan, you have to look at those together. So the third class of problem I want to talk about is, what if it's not your fault? What if the problem is just cluster weather, right? So here's an example where on the cluster, this same application was running multiple times, and we know it was the same application because in this case it was very simple. It was, Scala Pterosaur. This is one of the common applications. It ran 20 odd minutes multiple times in a row, and then one time it took well over an hour. Well, why did it take a lot longer? If you look at the Spark Web UI, there's no obvious reason for the delay. It's got the same data coming in, and it's got the same stages. It's just they took a lot longer. In the second time, they took a lot longer than the first time. Well, why did that happen? If you look at it in a time series, however, you start to see what's something interesting. Hey, the second run, the slow run, it was clearly the x-axis is time, and it took a lot longer. Right? This one was a lot quicker. But I also notice that the resources used in the fast run were significantly higher. Right? The y-axis is the same on both of these. And so the resource in the first run, in the fast run, it reached nearly the top at the beginning of the execution, where here it was significantly depressed. And at the very end of the job, right, the slow run started to get a high resource utilization. But for most of the lifetime here, this was significantly lower. Right? So that's a pretty big clue. So this might cause us to want to, hey, let's look at the cluster weather for this slower run. So let's look at the cluster load. And if we click on that, we can see, and in the next 3 slides I'm going to show, the slow application, the TerraSort in question, is always the green area. And the other colors are other applications running on the cluster at the same time. And so we can see, here's CPU. I can see this application, its attempt to use CPU is getting pounded down by this other application. It happens to be from a known user, and I can see what queue, and I can see what app it is. Right? So clearly, the reason this is slow is because this guy's pounding it down. Right? Similarly, I can also see that the memory here. This guy would like to get more memory, but actually it's not able to because there's other things on the cluster trying to use memory. In particular, this one is really killing it. Right? And even more, I can see HDFS, even its ability to read from the HDFS. This is how much HDFS read. Its attempts to read from HDFS are getting similarly pounded by this expensive application. So even something that looked like a small application, if it's trying to do a lot of HDFS, might slow down your application. And from your own application counters, that's very hard to tell. The product that I was just showing that basically puts these different things together and shows per app time series. This is actually in early access starting today. And it's free for development teams. If you're interested in this, or to give us feedback, please visit our booth, mail us, or go look at it. Other tools that I showed here for links for looking at this presentation later, Dr. Elephant. I would highly suggest people take a look at that, and the enterprise version of the application profiler is also a link for that. So basically, to recap things that we talked about, use things like Dr. Elephant application profiler. Use heuristics to find very known problems, right? Things that have happened before. When you want to find more difficult problems, having the join of the execution plan plus a time series is an extremely useful visualization. And then also make sure that you can look at the cluster weather so that you don't spend a lot of time debugging things that actually weren't your app's fault, right? Because you'll never find it. Last thing I'm going to do is just mention some talks that I'm interested in that come over the next couple days. So a more detailed view of the code analyzer. Vinod from Pepperdine is going to talk about that tomorrow. Also a different project that we're very interested in and participating in, as well as several other companies, is the Spark on Kubernetes and HDFS on Kubernetes. If people don't know what Kubernetes is, it's a new cluster, container-oriented cluster manager that came out of Google, but now has lots of companies participating in it. And there's a Birds of a Feather session tomorrow at lunch. So please join us. And I see Eric from Red Hat over there, and others if you're interested in finding a new way to run Spark applications. Anirudh and Tim are also going to talk about specifically the Spark on Kubernetes in a talk tomorrow afternoon, how that works. We've also got to talk about how HDFS can be made to work with high performance on Kubernetes. There's actually some tricks there. So we're going to be talking about that Wednesday morning. And then also Wednesday morning, there's going to be a presentation from LinkedIn and us about more details about how Apache Spark and Dr. Elephant work together. Thank you. That's the end of my talk. Questions? Let's throw you one.
Hello. Here.
Hey, Sean.
Hey, Shankar.
So quick question on the code analyzer. So you mentioned the other applications are bringing down your application's memory. Don't you get reserved memory when you ask for an executor, right? Like, how does the other application influence how much memory you use?
So in this case, by the way, our question asker is from LinkedIn, is one of the principals on Dr. Elephant. So if you like Dr. Elephant, you should say thank you to him too. So in this case, what was happening was less executors were actually getting, the executors were getting allocated more slowly. And it was, there were, at the scheduling layer, there were, the Spark app wasn't getting all its executors. This was hard to tell if you don't look at it as a time series, right? Because when you look at the counters in the end, it did all the same work, right? But if you actually were looking at a time series, included either, any memory metric, or if you just looked at the count of executors over time, you would see immediately, well, this one has less.
Okay, so that graph was aggregate across all executors?
Yes, it was.
Okay, got it.
So I think the plot you're talking about, come on, was this one, right? And so this was aggregated across all the executors, like you said, right? How much memory was this application actually able to allocate?
Cool, thank you.
Yeah, I was just wondering if you could go over quickly some of the main levers we have to improve performance as we're identifying issues. So you mentioned allocating more memory, partitioning. What are the levers?
Yeah, so some of the most there's a bunch, right? Or at least a handful. So common things that you would look at, there's configuration layer things, right? I talked about, using the cryoserializer, right? For example, making sure to have an external shuffle service. So, and when things die, or when, there are several reasons you might want to have an external shuffle service. Another key, lever is how much memory you give to your, JVMs and to the various regions within the JVMs. Right, so there's several different ways that memory gets used, and you have to pay attention to how they're getting, which part is using the memory and how much you're giving it total. You don't just want to give it more and more and more, because that impacts other things on the cluster. Another thing is the task, how they're distributed to executors. If there's significant skew, that can be a problem. Frequently, the answer there is to increase the number of partitions. Right, so if you have twice as many partitions, the chance that one hot partition, right, the data will get divided up evenly among its hash space. But if some elements of the hash space are significantly bigger than others, then those executors might have to do more work, right? Or in our example here, if you have so few executors that it'll be so few tasks, partitions that where's my example? Come on. Yeah, here, that, it's 1, 1, 1, 1, 2, right? That 50%, that 2x difference is a significant skew, right? So in this case, increasing the number of partitions maybe a little bit, not a huge amount, 2x, 3x, so that you can divide up the work more flatly will be a win. Those are the most common ones. The other things might involve looking into your actual code, right? And the main thing there is to figure out which stage in your code might actually be the thing to look at to see if there's some problem where you're causing key skew. Right? The common case there is the null key, right? That if there's a lot of things that fit into some particular default key, that executor is going to have a problem. Whatever executor serves the downstream task from that in the next stage.
Any other question? My Fitbit is going to make some work today.
What are some of the best practices to avoid some of the common problems that you discussed?
Well, I have to say the very first thing is just get the basic configurations right, and there's two ways to go about that. Obviously, one is to try to attend every conference and every talk and find every single best practice that you can. And you should all do that, but that's hard, especially hard to keep track of all of them, which is why Dr. Elephant obviously codes them into a thing, which will tell you, right? And it's a living, the part of the point of Dr. Elephant and especially the application profiler, where we take care of the upgrades, is to keep track of what the best practices are and just repeatedly tell you, maybe you're missing something here. In your configuration. The other things to typically look at are skew, right? Skew is a big performance killer. Garbage collection, right? Clearly, if you don't have enough memory and you're spending a lot of time in GC cycles, that is frequently a big red flag. Obviously, I gave an example here where that was a false flag, but it is, so there's a reason people look at that one, because garbage, running out of memory does, if it doesn't crash your app, it can cause extreme slowness in any Java-based application, which Spark certainly is.
Oh, there you go.
Hi. We know that the driver process works as a centralized
Yes.
orchestrator to launch different processes to different executors. How we can guarantee a fail schema for the driver processing Spark, and does this tool alarm in case a process or a driver process goes down?
I'm sorry, in case a driver process does what?
Goes down?
Goes down. So, okay. If the case of the driver process goes down, that's basically going to translate to an entire Spark application failure, right? So if the driver process dies, you're right about the driver process being central. And currently, if this driver process goes down, the Spark app generally dies, right? I think that there is some concept of advanced work of some kind of reliability there, but I'm not aware of anybody who's using that. I'm not even sure if it's ready to use. So in general, if this dies, it doesn't translate into a performance problem. It translates into an application failure. So in that case, you can see it in multiple places, right? Certainly, our tools, the application profiler, will show that. It'll also show up as a failure in the Spark Web UI if you look there. That's a common case enough that in you can make an alert for that kind of thing in products like ours.
We'll take one more last question from there. Go ahead.
My question is whether Dr. Elephant saves information about the past tasks or jobs that have been running. Well, I'm asking this question because I remember one of the optimization parameters is number of CPUs per executor, and it really depends on the architecture of your hardware, of your cluster. So. Yeah, so Sandy was talking about 5 executors, or 5 cores per executor, and on other architectures that we currently use, we have like about 8, but we have larger, anyway.
Yeah, that's a good question. There's actually been some discussion in specifically the Spark, Spark heuristic track for Dr. Elephant about making a heuristic that talks about, here's a good number of CPU cores. But of course, it's hardware dependent, and so you might need to tune that. So I'm actually hoping to take advantage of all the telemetry that we collect to try to figure out a good, way to compare the hardware to the recommendation of how many cores you have to try to make a great heuristic there. But back to your question about what does Dr. Elephant store? So Dr. Elephant actually runs, it has a section that is talking to the Spark history server to pull data, and then it computes some heuristics based on that. So it data reduces significantly. It doesn't restore all of that data. It reduces what it got out of the Spark history server, which is basically the Spark event log. And then it stores in a separate SQL database. So you have to stand up a side SQL database, but it stores in that the results of this data reduction. What things it data reduced and what heuristics fired. And then the UI is actually just a view on top of that. It doesn't store all of the raw data. So if the raw data that you were happening to looking for was in what it stored, then you could figure it out from its database, but it's definitely not the full fidelity. Part of what we're trying to do with the application profiler is store everything that Dr. Elephant does, but actually also have all of our cluster history so that we can look back and try to figure out exactly what you're talking about.
Well, give a big hand to Sean. Thank you very much, Sean.
Thank you.
Thank you. Dan.
All right. Mm-hmm.
Now, today, if you were to go to any big data conference, such as this one, or a machine learning conference, invariably there'll be a presence and domination of talks about machine learning and talks about deep learning. And you might ask, well, why now? Why not 10 years ago? And I think many would argue that we have actually made huge strides in how we actually distribute computing at scale. Not only the deep learning and machine learning frameworks that allow us to do massive parallel computing of real time, but also allow us to do prediction at a fairly accurate level. But there's a problem, people would argue, is that how do you actually deploy those machines, and how do you deploy those training models at scale? And to tell us all about how do you actually do that is Dan Crenshaw, who is the doctoral candidate at Rice Lab. And those of you who don't know what Rice Lab is a successor of AMP Lab at UC Berkeley, which actually gave us famous projects like Apache Spark and Mesos and Tachyon, which also today is known as Lexio. So give a big help to Dan from Rice Lab.
Great, thank you. So my name is Dan Crankshaw. I am a PhD student in the RISE lab. I was in the AMP lab for the last 3 years of the AMP lab's life. And now I'm helping carry that momentum forward. And today I'm going to be telling you about a system that we've been building called Clipper, which is a system for serving machine learning models. This is joint work with a bunch of great collaborators, all the way from undergrads to senior faculty. Everyone, this work wouldn't have been possible without all of them. So let's get started. So generally when people say, I'm going to give a machine learning talk, they're often talking about the training process. I know there's a whole machine learning track here. I imagine that most of those talks are going to be about training models in various ways in different models. So that's this process of taking some large data set and then using some system, potentially like Spark, to train some model. The result of that training process is a model, which is just a function that takes in some input, perhaps an image, and produces a decision. For example, it might tell us what's in that image, tell us that there's a cat in that image. And then once we've trained these models, we generally want to do something with them. And a really common thing that people want to do is use these models to make real-time decisions, to power interactive applications. So for example, I might want to use a model that I've trained to look at queries that are coming in as users interact with my application, and use that model to decide potentially what content to show them or whether to let a transaction go through or not. And it's this serving process, particularly this low latency serving process that I'm going to be focused on today. So I'm going to be telling you about the challenges and then a system that we've built to do low latency prediction serving for interactive applications. And when I talk about interactivity and low latency, I'm talking about on the order of milliseconds to tens of milliseconds within the human interaction boundary. So in this talk, I'm going to talk about three things. The first is that I'm going to give a little bit of a layout of how we view the challenges of prediction serving. Then I'm going to give an overview of Clipper, talk about its architecture a little bit, and how we address these challenges. And then finally, I'm going to talk about how you can use Clipper to deploy and serve Spark models in production environments. I'm going to give a little demo of doing that. So let's get started. So prediction serving raises some new challenges, both algorithmic and systems challenges. And there's two that I want to highlight. The first is the need to support low latency, high throughput serving workloads. And the second is how to deal with the large and growing ecosystem of machine learning models and frameworks. So what's challenging about supporting these interactive serving workloads? Well, one thing is that models are getting more complex. State-of-the-art models can take tens of gigaflops to make a single prediction. This model that I have up on the screen, this is the architecture for GoogleNet. It was a state-of-the-art computer vision model maybe 2 years ago, and it was actually designed to be a simple model. It was designed to be fast. State-of-the-art models like ResNet or something have 155 layers, 152 layers. These things take a long time to make a prediction. And this is critical because these models are being deployed on the critical path. We need to make a prediction with these models between the time that a user initiates a query and responding to them. And we need, because they're on the critical path, we need to maintain SLOs, things like latency SLOs, even under heavy workload or bursty workloads. To address this, people are starting to turn to specialized hardware, using things like GPUs and even more exotic silicon to manage these workloads. For example, if we look at Google Translate, the Google AI team likes to talk about the work that they do. They like to publish it, which is great because now we can sort of understand what they're doing, and they really are pushing the state of the art here. Google Translate is truly a miracle of the modern world. There was a New York Times article a few months ago that interviewed some of the people at Google that are doing AI, including the translation team. And in that article, they say that they translate something like 140 billion words a day. Well, we can look at the cost of making predictions with Google's state-of-the-art translation system by looking at the papers that they've written. And it turns out that would take something like 82,000 GPUs running 24/7 at minimum just to serve these workloads. This was so expensive that Google actually invented new hardware. They invented these TPUs. These are these ASICs that Dave Patterson and others were involved with just to score their machine learning models, their deep learning models. TPUs, they're not used in training. They're just used once you have your trained model and you want to power these workloads. And Google is sort of at the boundary of the state of the art, but this approach is somewhat typical of big companies or big systems. They build specialized one-off systems for high-value products. And this works well, but it's kind of limiting. There's some problems with this approach. So one is that it's just expensive to build and maintain these applications, not just from an engineering standpoint, but also because it requires they're highly specialized and they require both machine learning expertise and systems expertise coordinating and working together to build these applications. The result is a tightly coupled model and application, which makes it difficult to change or update models. It makes it hard to experiment and iterate. And often they only support a single machine learning framework and aren't very general purpose. And this is problematic because of our second challenge, the fact that there's this large and growing ecosystem of machine learning models and frameworks. And I'm going to argue that this ecosystem and the fact that it's growing, it's not a fragmentation problem, it's a rich ecosystem resource. The fact that there's all these models and applications is a good thing, and we should be taking advantage of them. But why is it challenging to support all of these things? Well, let's take a single example. Say I want to do fraud detection. I might start with training a Spark model. That gets me pretty far. But maybe I have some more rich content from users. Maybe I have some natural text, some natural language, some images maybe, who knows. And I want to bring in a deep learning model as well to help me improve my fraud detection. Well, already, if I want to bring in Spark and TensorFlow and use them for the same application, I have to deal with the fact that I have different programming languages. TensorFlow is written in Python and C++. Spark is JVM-based. I have to deal with different hardware. Spark is going to want to run on CPUs. TensorFlow likely is going to want to run on GPUs. And I have different costs that I have to deal with and sort of manage and balance the throughputs of these different models. And of course, we don't just stop with fraud detection or just with Spark or just with TensorFlow. We have applications like content recommendation, personal assistance. I think Apple just announced a new Alexa, Google Home competitor today, actually. It seems like these things aren't going anywhere. Robotic control with things like self-driving cars, machine translation, and so on. And of course, we have lots of different systems that people are using. Some of these are highly specialized for particular applications. Some of them are more general purpose. And we have this sort of all-to-all dependency structure that makes it hard to build specialized solutions for each system or each application. So if building new serving systems for each framework is expensive and hard to do, what do people do? Well, a common approach is use existing systems as well as we can. So generally, this looks like doing offline scoring, where I extend my batch analytics process to both train the model and then label all of the inputs that I might possibly need to make a prediction about offline ahead of time. I can take these pre-materialized predictions and stick them in a database, some sort of key value store, and now I've transformed my prediction serving problem, my model serving problem, into a data serving problem. We know how to serve data scalably at low latency, so I can achieve my performance goals, but of course, this leads to problems as well. The biggest one is that it requires the full set of queries that I want to make predictions about ahead of time, which essentially means that I'm limited to small and bounded input domains. This works fine for things like content recommendation potentially, but it's not going to work for fraud detection. We're going to need to do that offline after the fact, and that means that we can't do it in interactive applications. It leads to wasted computation and space because I'm rendering and storing unneeded predictions sort of just in case. And then finally, it's costly to update because I have to rerun this batch job every time I want to make new predictions. So there are some good things and some bad things about, so there are some serious challenges that face us around prediction serving. And I talked about some ways that people are solving these challenges today. And we think that there's some pros and cons of both approaches. So what we aim to do is unite these two approaches, take the benefits of highly specialized systems, provide high performance, on-demand prediction serving, but provide the generality that offline scoring provides, and unify these two approaches. And that's sort of precisely the role that Clipper plays. We do online prediction serving, we render predictions as needed, interactively, but we can do it for any system. So what might that look like? Well, we have this large, rich ecosystem, lots of models, lots of applications that I keep showing you. The first thing that we probably want to do is isolate these systems from each other and encapsulate them in isolated environments. then we probably want to get rid of all of this mess in the middle and decouple these applications from these models so that they don't have to know the details of each other. And then we want to maximize their performance. And that's exactly what Clipper does. Clipper is a system that sits in between your applications and your models. It decouples them. And then it inserts some functionality in between these two things to maximize the performance of each of these individual systems in a general purpose way. And that's what we'll spend some time talking about. I am an academic. I'm a PhD student, but this is real software. The core system is about 35,000 lines of C++. It's open source on GitHub. And we're really putting a lot of time into building this into a real system. And the goal here is to have a community-owned platform for model deployment and serving that can help everyone take advantage of this rich ecosystem of models rather than causing people to fragment into these different walled gardens. So when you actually deploy Clipper, there's a few things that happen. So this piece that I keep showing you is actually what we call the query processor. This is the thing that your applications talk to through a REST interface. There's also some other pieces involved. There's a management process that sort of manages the configuration and running of this distributed system. And then we store all of our persistent state in Redis. We believe pretty highly in Dockerized and containerized deployments. We think that simplifies a lot of things. And so all of these things run in Docker containers. Then, of course, you have your model containers. And these communicate directly with Clipper. They isolate each model, each framework, in its own environment with its own physical and software resources that it needs. And these communicate directly with the query processor. And then finally, you can manage all of this with a client library that we've provided that you can install with pip, and then you can run on your laptop. So you don't have to deal with compiling or try to simplify cluster management as much as possible. Zooming out a little bit further, the Clipper slots into your serving application as just another microservice. You query databases from your web server. You might query other downstream services. You might query things for business logic, for authentication. Our hope is that you then query Clipper to make decisions for you. And that should fit in seamlessly with existing production serving infrastructure. And then our goal is to connect the analytics cluster with the serving cluster by serving as a mechanism to bridge these two frameworks by taking your models trained in your analytics clusters and deploying them directly into your serving system. We hope that it's pretty easy to get started with Clipper. I hope I'm going to demo that in a little bit. All of our Docker images are available on Docker Hub. You can install this client library with pip install Clipper admin. And the nice thing about this is that you can get up and running without having to clone anything or compile anything or deal with dependency management or anything like that. It should just be as easy as pip install. So now I'm going to talk a little bit about some of the technologies inside Clipper and how this system actually works, which is what we spend a lot of time doing the research on. And in particular, I want to highlight three things. One is how we use this containerization, how we use Docker, as I talked about, to unify all of these different pieces of software. The second is how we can use classical systems techniques like caching and batching to optimize performance. And then the third is how we can enable data scientists to compose models and actually improve application accuracy in the serving system. So going back to this high-level view of Clipper, I want to start at the bottom and talk about how we use containers. So first of all, why did we use containers in the first place? Well, we had two demands that needed to be met. We needed some sort of common interface that all of these different machine learning frameworks, written in different programming languages, could expose to Clipper so that we didn't need to do a lot of work to implement a new framework and deploy a new framework into Clipper. And then the second is that we think it's really, really important to evaluate models when you make predictions to use the same code and the same systems as you did during training. And the reason for this is that doing machine learning today is sort of a bug-prone, error-prone process. Traditional programming language tools aren't sufficient to catch all the bugs that happen when you build your machine learning models because you're combining not just code, but also data. So you can have code that runs perfectly fine, but if you put garbage in, you're going to get garbage out. And so in order to reduce the surface area of these bugs, we think it's important to reduce code duplication as much as possible, follow sort of machine learning best practices, and leverage the fact that these machine learning systems are often being highly optimized for performance. And so it's unlikely that some other person is going to come in, be able to actually get better performance out of some of these systems. So how does this actually work? Well, if you want to stick a new model into Clipper, you implement this model API, which we hope is really simple. It's basically two functions. This is an example in Python. You have an initialization function, and this basically informs the system, how do I load my model into Clipper? This allows you to do things like any sort of initialization code, talking to databases, but the primary thing here is generally deserializing your trained model and initializing it so that it's ready to make predictions. Once you've done this, you just specify how to use that model to make predictions. We've implemented, or we support this abstraction, this interface, in a few different languages. We have support for Python and Java right now. We have preliminary support for C++. We actually have an open pull request to add support for R. And the observation here is that, as I've said, frameworks are written in different languages, and we should support all of these things. But by making this model container API lightweight, it's not a lot of work to support a new language. So once the data scientist has implemented this container API, they package it along with all of its dependencies. So for example, if you're building a Spark model container, along with Spark in a Docker container. Then this Docker container, as part of this model interface, has a little RPC client embedded in it that knows how to talk to Clipper. So that's how you deploy a model into Clipper. But because these models are running in their own containers, we can have many of them deployed at once without interfering with each other. We can actually have them distributed all across a cluster if we want. So along with sort of benefits to the abstraction and providing flexibility that this containerization provides, it actually also has some performance benefits. By running models in separate processes as Docker containers, we get resource isolation, which can actually be kind of critical because we're in this exciting new field of machine learning and people are pushing out new systems and new software all the time. And sometimes these things are written by academics, and sometimes they have bugs in them and they segfault. And if one model segfaults, you don't want it to bring down your whole system. You want to isolate it. And then it also provides a convenient mechanism for scale out. If I need more throughput from, say, an expensive TensorFlow model, I can just replicate this container, and all of a sudden I have more throughput. We get horizontal scaling. Now, we did stick an RPC call in between, an additional RPC call in the query serving fast path. And earlier I said, we need these things to be fast. They're deployed on the critical path. So we wanted to understand what was the overhead of this additional RPC call. So we compared Clipper's performance to TensorFlow serving. TensorFlow serving is a great system from Google designed to serve TensorFlow models. And in contrast to Clipper, it runs as a single monolithic system where sort of all the serving infrastructure runs in a single process, so you don't have this RPC overhead. And because Clipper can serve TensorFlow models, we could sort of do an apples-to-apples comparison. So we trained several TensorFlow models and compared throughput and latency on them. The example I'm going to show you is an AlexNet model, but we went both lighter weight models, and we also evaluate this on an Inception model, which is pretty heavyweight. And essentially what we find is that the throughput and the latency are pretty comparable. So the takeaway here is that the performance gains from a monolithic design, while they might exist, are pretty minimal. And we think that the advantages of a containerized system allow us to do a lot more across these different frameworks and present a much more general purpose system. So how do we maximize performance in a general purpose way? So I'm going to talk a little bit about how we use caching and batching to get these performance gains. So the critical thing here is that this happens in the main Clipper process, in the query processor, above these model containers, which means that Clipper doesn't have to know anything about a particular model container to apply these techniques. So the caching we do is pretty straightforward. There's not that much exciting to say here, except that it's really, really critical for certain applications. But cache. What I want to talk about a little bit is how we do batching. So why does batching improve throughput? So one reason is that a single page load might generate many queries. So we often have these bursty workloads that could benefit from batching. And the second reason is that these frameworks are generally throughput optimized. And so as you increase the batch size, you get this great scaling in throughput, which means, part of this is from using specialized hardware like GPUs, which do well with batches. And some of it is just data parallelism that the designers of these frameworks have implemented. The tricky part here, though, is that the optimal batch size depends on the hardware configuration, the model and framework that you're using, even the current system load. So these things are changing all the time. And the trick is to find the right spot on that curve. So what we do is what we call latency-aware batching. Basically, we want to increase the batch size as much as possible to maximize throughput. But we also have these latency SLOs that we need to meet. So we basically adaptively trade off latency and throughput, increasing the throughput until we exceed our latency objectives and then bringing it back down. One simple example of how we do this is an additive increase, multiplicative decrease scheme. We increase the batch size until the latency objective is exceeded by additively increasing the batch size, sort of probing the limits of the system. And then if we exceed the latency objective for a particular application, we just cut it by a little bit and bring it back down. And this allows us to sort of adaptively, but pretty efficiently hone in on the right batch size for the given conditions. It turns out that even these really simple things work really well. This is just an example from an NSDI paper that we wrote this spring. We trained a bunch of models and a bunch of different frameworks. They have different computational costs. And basically what you see is the darker lower bars are without batching, throughput that we can get without batching. And then the higher bars are the throughput increase that we can get from using this adaptive batching mechanism. And essentially what we see is that we get over an order of magnitude and throughput improvement from batching in almost all cases. In some cases, it's 20, 30x throughput improvements. So batching is pretty critical, and we found some simple general purpose ways to do batching in a latency-aware way. So finally, I want to talk a little bit about how Clipper does cross-framework model composition. And this is what allows us to express things like ensembles, bandit methods, other classical machine learning techniques that can improve accuracy of your applications directly in the serving system. So this is in the purview of the selection layer and is governed by what we call selection policies. So basically what selection policies do is they allow you to compose or to use predictions from multiple frameworks at once or from multiple models at once to improve accuracy. So why might you have multiple models? Well, one is people are generally doing periodic retraining. This is a very common pattern. So you might want to figure out, is version 2 actually better than version 1, and sort of play them off each other. You can think of multi-arm bandits as sort of a fancy way of doing A/B testing. But also, as I've mentioned before, data science is an iterative process. This is one of the problems with building these specialized, complex, highly engineered systems is it's hard to iterate. And we want to support this type of experimentation. So data scientists are constantly experimenting with new models, new features often, even new frameworks sometimes. So you might have multiple models because your data scientists, either with the same person or different people on a team, are experimenting with different technologies or different techniques, and they want to figure out which ones are actually better or worse. So for example, one thing that you can do if you have multiple models is use these models to estimate confidence. We can send a query to all of these models, look at their predictions, and if they all agree, we'll predict cat, and we can be pretty confident about that. And we can express that confidence to the application, to the client. On the other hand, there might be more complex examples. Some of these models might predict cat, others might predict man, or t-shirt, or space, or who knows. We'll still provide a prediction. Cat is still the majority label, so we'll still provide that prediction. But we can communicate that we're uncertain about this prediction, and a client application might use that information, these additional semantics about the prediction, to make different decisions. So we did some research to explore different types of selection policies in some work that we did this winter. We looked at this confidence estimation policy. We also experimented with some different multi-arm bandit algorithms to see if we could learn the optimal model or combination of models to maximize accuracy, and also to deal with models that degrade in accuracy and recover from these degradations. And then also we did a little bit of work on figuring out if we can automatically personalize models or personalize predictions across machine learning frameworks. And there's some more details here in the Clipper NSDI paper. So this is sort of an overview of how Clipper works and some of the technologies, some of the research that we did to make this general purpose system work well across many applications and many frameworks. Now I want to talk a little bit about how you might use Clipper to serve Spark models. So as I mentioned, we want to make it really easy to bridge your analytics cluster, the thing that's training your models, with your serving infrastructure. I'm not going to talk about how you sort of get a Clipper cluster up and running or how you query it. I'll show a little bit of a demo of that in a couple minutes. I want to just focus a little bit on this arrow. So I mentioned earlier, you can always implement your own model container. And we actually did a fair bit of work to try and make this as simple as possible. But it does involve building a Docker container and some other steps. And for common use cases, for things like Spark and scikit-learn, we wanted to make it even easier. So we spent some time, and basically we implemented some methods so that this Clipper admin, this thing that runs on your laptop or runs in your analytics cluster, this little Python library, can automatically deploy Spark models directly from the training job. So we have this API, clipper.deploy PySpark model. I'm going to show you the PySpark version. And it takes some other metadata as well as arguments, but the important things here are that it takes two arguments. It takes a model, and this is your in-memory, your in-JVM instance of your PySpark model. It can be an MLlib model or a pipeline model. And then it takes a predict function. And this predict function is a Python closure that takes a few arguments. It takes a Spark session, it takes the model, and it takes the inputs that you want to make a prediction about, and you can read more about that offline. But the important thing here is that by providing not just a model, but a closure that can wrap that model, we enable you to express things like business logic, featurization, pre- and post-processing, because it's rare that what you're doing is deploying a raw model that encapsulates all of that in itself. There's always stuff that you need to do before and after your predictions. And we think it's really important to support that. So, for example, you might have an MLlib model, an SVM, and I might write a little prediction function, this prediction closure, that first normalizes the inputs. This is calling out to another Python function that's also going to get captured and put in the model container, and then calls model.predict on the normalized inputs. When I call PySpark.deploy model, I'm giving it the SVM and the simple predictor function that I just wrote. I can do the same thing with pipelines models. Here I have a fancy predictor that does some JSON parsing, calls pipeline.transform on my model, and then I've defined a pipeline that has 3 stages that aren't shown. Same API, I call clipper.deploy PySpark model. I give it the in-memory pipeline. I give it my Python closure, and it gets automatically deployed. And what's happening here is that I'm going straight from a model that I've trained in my Spark cluster directly to the serving system. I'm taking my model, I'm wrapping it in a container, and now I've deployed a model to Clipper, and I can serve it without having to deal with any of sort of this messiness of serialization. We have some APIs to do this for some other types of models. We can deploy arbitrary Python closures like this as well, which means that we can deploy scikit-learn models in the exact same way. And in fact, we can deploy anything that's pickleable. The reason that we had to sort of special case PySpark is that while PySpark models are serializable, they can't be serialized with the default Python pickling infrastructure. You have to call Spark's own APIs. And then we have an analogous API if your models are trained in Scala or in Java. That also supports both the RDD-based and the data frame-based API. So now I still have a couple minutes, so I'm going to give a demo. Everyone cross your fingers, of training a model in Spark and then deploying it to Clipper exactly like I just showed you. Hang on. Okay, so I'm going to do this in IPython, and I didn't, there's no code backing this. This is an IPython notebook that's online. I have a link to it later. I didn't clone anything. I didn't have to build anything. This is just a fresh Anaconda environment. So I'm going to import some of my standard libraries, and then I'm going to pip install Clipper. I'm actually going to cheat because I already pip installed it in case the internet didn't work. But this just pulled Clipper admin from PyPy. So now that I've installed it, I'm going to import this Clipper connection object from the package. And then I'm going to create an instance of it. So this Clipper, creating this Clipper instance on localhost is just going to create a connection to the machine that I want to deploy Clipper on. It's not actually going to initiate anything. So you can see when I run that, it's going to check that Docker is running. I have Docker running on my laptop, but it didn't start anything. To actually start Clipper, I'm going to call clipper client.start. Hopefully this doesn't take too long because I have the Docker images already downloaded. But this is just pulling Docker images that are published to Docker Hub. So now I have Clipper running. I have those 3 processes, that query processor, that management front end, and Redis running on my laptop in Docker containers. And now I can start to interact with Clipper, I can start to query it, and I can deploy things to it. So I can query it. This is inquiring for all the registered REST front ends that I can make predictions on. I haven't done anything yet. This is a fresh instance, so we don't see anything. But now I can go ahead and register this application. An application is sort of Clipper speak for a prediction REST endpoint. So I'm going to give it a name. I'm going to name it digits. I'm going to tell it that that it should be querying the PySpark SVM model, which is actually going to be a logistic regression model. I'm going to tell it that it should expect inputs, the inputs to this REST interface to be ints. And then I'm going to give it some other metadata. I'm going to tell it what to do if it can't get a prediction in time. It's going to return a default of -1. I'm going to tell it the latency deadline that I want for this application. So I registered that. That worked. Now if I query to get all apps, I can see that this digits app was registered. And now that I have this REST interface, I can query it, and I can get a prediction. So what do we see here? We're seeing that this default field was true. That means that Clipper responded. It provided a prediction, but it was the default prediction that I registered up here. And now I can see why it responded with a default prediction. And the reason is that we haven't connected any models to this application or to this endpoint yet. So Clipper is going to respond. It doesn't care if there are models or not, but it can't actually make predictions without models backing it. And so then we see that the actual prediction is this -1, which is what I told it to do if it couldn't find a model to make a prediction. So now we're sort of switching boxes and training a PySpark model. So I'm going to import PySpark and create a Spark session. And now I'm going to define a little training pipeline. Well, not a pipeline. I'm going to use an MLlib model. But I'm going to define some featurization functions and things like that. I'm going to parse some training data and load it into memory. So this normalization function is just normalizing each feature vector independently by subtracting off the mean. I'm going to train an MNIST model, so I'm loading the MNIST dataset, which is sitting on my laptop. And I've created a training RDD, which is an RDD of labeled points. So now I can train a logistic regression model. This is calling Spark locally, but you can imagine that this is calling out to a Spark cluster. And that's going to take a second. So once that's done training, we're going to then switch into deploy to Clipper mode. And so now we have to define 2 things. We have to provide a model and this predict function that wraps the model in any sort of business logic we want to provide. So that's what so the model we're training right now, so we got that covered. So now we're going to define this simple predict function. It's going to take in a Spark session. The reason it takes in a Spark session is in case you need to create a data frame, for example, if you have a pipeline model that requires data frames as inputs. We're going to not use the Spark session for our predictions, but we are going to call normalize, which was this function I defined up here. And when I deploy this model to Clipper, this simple prediction code will be serialized, and will automatically recursively serialize this other function that I defined as well, and so on. So that all the dependencies will get serialized as well. So this model got trained, so that's good. So now we're going to define our prediction, where we're going to normalize each input independently, then call model.predict on that input, and then return each prediction as a string. We can test that by randomly generating a data point, and we see that our prediction function works. So that's good. We want to debug it before we deploy it. And now we can deploy this model to Clipper. We're going to call deploy PySpark model, just like I showed you earlier. We're going to give it the model a name, PySpark SVM, even though it's a logistic regression model. We're going to give it a model version. And then we're going to specify this prediction function that we defined earlier. This is your prediction closure. We're going to give the model. This is this in-memory PySpark object. We're going to provide the Spark context, because Spark needs that in order to serialize these models. And then we're going to provide some metadata about the inputs that this model expects. That allows Clipper to do type checking between models and applications. So Clipper in the background is going to do some verification that your Python packages that it's trying to deploy are all compatible. And actually, Nishad, who's one of the undergrads working with me, who wrote that code, is sitting back there. If you have questions about getting Spark and Anaconda and all these things working together, which is not as easy as I wish it was, you should talk to him. Then we serialized the model, and we published it to Clipper. And Clipper loaded the model. And now, when we query that same digits endpoint, that same application, we see that we get a real prediction back. This default field is now false. Our model predicted 1 as the prediction, and we have this new query. We can query it again. It looks like randomly generated predictions are generally 1. And it's as easy as that. So we're pretty excited about this, and we hope that you check it out and that you play around with it, and I'm sure break things and file GitHub issues and things like that with us. So now let me wrap up and let my computer think about how to load PowerPoint for another second. Okay, great. Yes, please check out Clipper. Our website is clipper.ai, which I registered by going to a very, very sketchy domain name registrar and putting it in my credit card. But we got a cool domain name out of it. So what's the state of Clipper right now? We had our alpha release of the system. We've been open source and sort of usable since February or March. But we had our first alpha release of the system that went out a week ago. There have been some bug fixes in between, so we're at 0.1.3, and this is available. The demo I showed, there's a link to it from the website, and there will be a link in there's a link in the slides as well, but you can run that. This is totally independent of Clipper's development environment. You need a Python installation, basically. In the alpha release, we have first-class support, like I just showed you, for scikit-learn and Spark models, which allows you to deploy directly from your analytics cluster without having to deal with model serialization and writing your own Docker containers. We're actively working with some early users to get them running Clipper in production. And we encourage you all to check us out as well. You can post issues or questions on GitHub. You can subscribe to our mailing list. This is something that we really believe in and we think can be really useful. And so we want to go the extra mile and try and help everyone help a community get started and help people be successful. In terms of what we have planned next, you can already deploy things like TensorFlow models today, but we have ongoing efforts to make it easier to deploy more and more of these common tools. We're always going to have this general purpose framework. You're never going to have to go through our API to deploy a model because we want, some random academic who's the world expert in some particular type of graphical models to deploy his software to Clipper. But for common things like Spark and scikit-learn and TensorFlow and Caffe, we want to make it even easier. We have worked right now on being able to deploy R models. We're working on Kubernetes integration to make it easier to get Clipper up and running in a production serving infrastructure. And then we're working on taking this this research that we did on these selection policies and bringing these bandit methods and online personalization and some ongoing work that we're doing on things like cascaded predictions into the serving system. This is research that we've done and that we've implemented and have promising experimental results on, but haven't made their way into, into the open source code base yet. And we're actively looking for contributors. There's lots of stuff. I don't have a team of software engineers that I've hired. We're grad students, we're academics, so we can always use more help. But we're very welcoming, and there's lots of exciting stuff to work on. So check us out on GitHub, check out our website, try and use it, try and break it, and send me emails if you have questions. So with that, I think I'm actually under time because we had this very long time slot. So thank you all for your patience, and I think I have time for a couple questions.
Begin to Dan. Thank you, Dan. Questions? Yes?
Any proposal for Apache?
Say that again?
Any proposal started for Apache?
That's a great question. The project is too immature at this point for us to have thought about that very hard. It's not ruled out. We want to get some momentum. We want to get a community. We want to get a more stable system in place before we even think about sort of long-term. At Berkeley, in these lab environments, we talk about projects graduating the lab, which is they've achieved research success, they've built a community, they've gotten some momentum, and now it's time for them to transition out of sort of being known by the lab into sort of a more open source, things like Apache, and we're not ready for graduation yet.
Okay, thank you.
Any other questions?
Hey, so my question is about, so we talked about integrating the inference part of all the deep learning or machine learning systems, right? So are there any plans to integrate all the training phases? Because right now we saw like we do the training beforehand the inference phase, right? And then the Clipper helps us to integrate all the inference phase from all the different architectures.
Short answer is no. And it's no for two reasons. One is that there's been a lot of time spent building these systems. So we don't want to sort of try and turn Clipper into a training system on our own. We want to leverage all this existing work that sort of has, a system to serve machine learning models wouldn't have been a very successful system, even 5 years ago, because we weren't seeing successful, there wasn't widespread success of building machine learning models. And then in terms of integrating all the APIs of all these different training frameworks, the challenge here is that the training APIs are much bigger, they're much more expressive, and they just have a lot more surface area than the serving APIs. Mm-hmm. And so trying to unify them in a general purpose way, in the same way, is sort of, in my mind, sort of a lost cause, and it's not even clear that it's something that you would want to do.
Any other questions? Oh.
How do you handle updating the model for, let's say, training it a week after you have new data?
Do you mean, how do you, can you expand a little bit?
Let's say I have some data, I trained the model today. Tomorrow I want to retrain with the new data that I have. How do I update the model in Clipper?
Great. So models are versioned in Clipper, and your REST endpoint doesn't know about model versions. It relies on the data scientists deploying the right version of the model. So if you have a new version of the model, you deploy the new model with the new version, and that will sort of transparently take over and start serving predictions. This work that I've talked about a little bit with supporting things like bandit methods, the idea there is that you could deploy your new version of the model alongside your old version of the model and experiment and figure out, is this new version of the model actually better? But basically, you push the new model into Clipper and use these policies to figure out what to do about that new resource that you've deployed.
Okay, thank you.
Anybody else? Once? Twice? Oh.
So I noticed on the benchmarking, I believe the kernel support vector machine performance was not that good.
Say that again?
On the benchmarks that you showed, I think the kernel support vector machine was lagging a bit behind the other models.
Yes,
And do you
yes.
have-
Joey wanted me to remove that from the slides. So basically that's a slow model. So it's a kernel SVM. So before making a prediction with a linear model, it's doing this nearest neighbors calculation, which is just a big expensive model. That's fairly hard to accelerate on a GPU. That was a scikit-learn implementation. The scikit-learn implementation of kernel SVMs is not particularly performant. So that's why the performance lag. But it's sort of it's a performance problem independent of Clipper. It's just reflecting that the performance of that model was much slower than like the linear SVMs and the logistic regression models and the random forest that I was comparing it against. Does that make sense?
Thank you.
Basically, kernels are hard is the takeaway there.
You talked about bandit methods and cascade predictions for model selection.
Yeah.
I just wondered if there's any discussion of using training to build models to select the model, or why did you decide to go with that route?
So there is discussion of it. We think that there's lots of different sort of ways that you could build these types of models, and using existing training data is probably a useful resource that you don't want to ignore. The motivation for doing this type of experimentation with live feedback in the serving system is that training data that you have often, for better or worse, is stale, or it may not be representative of your live workloads. And so we think that you should push this experimentation sort of as close to the live data as possible, to get sort of the freshest feedback as possible. That being said, I think that there are really interesting questions around using both labeled and unlabeled feedback. So you have queries coming in that don't have labels, but you can still observe things about the distributions of them. Using feedback that you might be able to gather from people clicking or not clicking on things, or all the various ways that we can gather feedback interactively, and labeled training data that might be sort of gold standard or ground truth, and using all of these resources together to maximize accuracy. I think that's a rich area for research, and we're excited to work on it.
Well, give a big hand to Dan Crenshaw from Rice Lab. And just